Huh. I hope this records. Okay, we're going to try again. Okay. Okay. Nice new seat. So, we've got a quick bell work problem. It is a Wednesday, and we have 5 things to do today after the bell work in your homework. So, hurry, hurry. And I'm wearing the headset today because I'm hoping I'll be able to capture today's class and record it as a video for first period that missed the class because they were taking PSAT. So that's why this is. But also, beware, the mic is hot. Okay. Luckily, the mic is hot but not very sensitive. Okay. This is nearly perfect, but I thought volume was 3 dimensions. That's right. Hi, why aren't you done? Hurry, hurry. Wednesday, hurry. Hey. Yeah, nice. Yeah. Hi, what do you need? Okay. Do you know where the pencil sharpeners are? Cool. There's one right next to Riley. Hi, how's it going? Oh, thank you for doing some work. Okay. I see. I see. I want volume as a function of x. And then I want a graph. Why don't you think about it algebraically first so that then you can make an easy graph? Okay. Yeah. That looks like a... That's not right. Yeah. Yeah. Where's the graph? Okay. You mean, can I just leave that off the graph? Yeah. Sure. Yes. Right. Yeah. Whoa. Oh. I love your volume equation. Okay. And you pulled out some negative 2's and got a positive 4. Yeah, that's great. Okay. That is? Yep. Okay. Okay. Hey, special task for you. Sure. Now that you've got this done, I want to ask you question number 3, and I'm going to ask you to present it to the class. What's the domain of this volume function? Okay? You what? Yes. Yes, true. great graph. Yeah? Yeah, perfect. Will you please present coming up with v of x, the equation? Okay. Will you please present coming up with the graph of v of x when he's done presenting coming up with the equation for v of x? Okay. Okay. Brian, you're up. Well, that wasn't on the board. That was it. Oh, was it? Oh, no kidding. Didn't know that. Okay. I'm sorry, I couldn't hear you over Alessandra. Y minus 2x. I agree that the length of the box will be 18 minus 2x. But the whole side is 18. Where did you get 18 minus 2x? I'm not disagreeing with you, but I don't feel like I got 100% understanding. Who can add some words? Ryan? Uh-huh. So this is the length he's talking about. This is the side of our box. Not this. He's got to do 18, the whole thing, take away these two x's. So he's got 18 minus 2x. Okay, go from there. Because when you fold those flaps up, those x lengths come together to make the height. That's volume in terms of x. Nicely done. Okay, David, will you show us how to graph that polynomial in factored form? Hey, Ryan, while he's headed up there, does anyone have any questions for Ryan about coming up with that equation? Okay. It doesn't matter to me. Oh, so because all the factors have a multiplicity of 1, we're just going to pass through, pass through, pass through? Okay, great. What? Can you label? Now, how did you know this would have the end behavior that it does, David? You got one end going down and the other end going up. How come they don't both go up? How come they don't both go down? How come it's not like this? Look at his equation. If you were to FOIL it out, negative 2x times negative 2x times positive x, what would that be? Positive 4x to the third. And so we've got a third degree polynomial, so we know end behavior looks like this with a positive leading coefficient, so it's not going to be this, it has to be this. Good. And you already talked about the multiplicity on each factor being 1, so we just passed through. Excellent. Don't go any further. That's all I wanted for the graph. Any questions about graphing from factored form? Okay. Quinlan, would you talk to me about the domain? It wasn't up there as a question, but it was in the homework last night. It's going to show up again in your life. I want to know the domain of this function. And some students say, well, Mr. Kukla, v of x is a polynomial, so the domain should be all real numbers. What are you talking about, a restriction on the domain? So what do you come up with? A negative value for x, okay? No negative, I can't cut a negative amount off the side of the paper. Okay? It would be exactly 0. Uh-huh. Why can't I have 7, though? Oh, so I'm cutting off more than I have for the whole side of that piece of paper or that piece of metal. Okay. So, and I also notice here, you had talked over here about I can't have any negative x's. Well, I also think I can't have any negative volumes for my box. Anytime my volume wants to be negative, I can't have that. But I really liked what you were saying about 7 doesn't work, because even though when I plug a 7 in, I can get a number, that number is going to be a negative number. And you pointed up here and said 7 plus 7 is 14, but I've only got 12. How can I possibly cut 7 off of each side? Okay, but what about over here?
That's the part that I can't remember, so if you can just take the logic out of my mind.
Sure. What happens if I want to cut 20, x equals 20 off of each side?
You have two problems here and here. So now you're getting into really weird.
Yeah, I just can't do it. Now I've got negative side lengths. And so this, even though this produces a positive volume, what's producing the positive volume is a negative side length times a negative side length times a positive side length. And I'm not that good a mathematician to be able to fold space to make negative side length boxes. So, not yet. So as a result, we're going to say, no, we can't have any of these numbers either. And so our domain is going to be this. Some people, like Brian, suggested that maybe this would be okay. Wasn't that what you were saying? Equal to 0? Who was saying that? Was that Dallin? Who said that? Somebody said that. You said that. So, and I'm going to accept either of these answers for our domain, because to me this is more a sort of philosophical question. Do you want your box to have the possibility of a volume of 0? No, I do not want my birthday present box to have a possibility of a 0 volume. That's a cruel joke birthday. Here's your dot. Instead, I like Quinlan's philosophy of life. No boxes should contain a volume of 0. But most math people write this answer because 0 is a real number, and I can have that dot box. But yes, good, nice, thank you. Any questions on this? Any questions from your homework worksheet that we should talk about? Going once? Twice? Basket of puppies. Okay, let's go. We have talked about what? You did. A basket of puppies. Just, there they are. Oh my God, there's so many of them. How do they have so much energy? I'm so tired, and they're not. Okay, so let's consider this for a moment. X to the 4th minus 13x squared plus 36 equals y. This isn't in factored form, but I'm supposed to graph it. I know the y-intercept is going to be 36 when I plug a 0 in for x's. I know I have an even degree polynomial with a positive leading coefficient, so I know both ends are going to go up. But I don't know how to graph this. So what do I need to do first here? Yes, sir. Do you remember how to factor that? Okay. How does that factor? So in his head, he said, I'm looking for the factors of 1 times 36 are 36. What are the factors of 36 that add up to negative 13? And he said those factors will be negative 4 and negative 9. He used our regular trinomial factoring technique here and did 2 steps in one. Okay, so he's got here and he's grouped them in pairs. What can you pull out of this first pair, Brian? Leaving me x squared minus 4. And from the second pair? A negative 9, leaving me again x squared minus 4. Are we done? What do we still notice? If I pull out the x squared minus 4, what's left over, Brian? X squared minus 9. But Nathan, these aren't linear factors. I still don't know how to graph this thing. What am I missing? These are both difference of squares, and I need to take this further. This is x minus 2, x plus 2, x minus 3, x plus 3. We know it's a 4th degree polynomial with a positive leading coefficient, so we know that both sides go up. We've got 2, we've got 3, negative 2, negative 3, and 0, 36. So Brian's right when he says the first thing I need to do with these is factor them. Because once I have it in factored form, no problem. Okay, and that brings us to this question today. What do I do when I see this problem? I'm supposed to graph this problem. X to the third minus 2x squared minus 5x plus 6. Is there a GCF here, Owen? No. Can I do factoring by grouping, Camille? Yeah, well, let's try. I'll group these two, and I'll group these two. Camille, what can you pull out of here? Okay. What's left over, Camille? Okay. What can I pull out of here? What can I pull out of here that will leave me an x minus 2? Shrug. So I don't think factoring by grouping is going to work for me here. So I'm kind of stuck because this doesn't want to factor. Well, no, because it's only, remember, it's called quadratic formula, not cubic formula. And so it only works on quadratics, but this is a cubic, so I can't use quadratic formula to find x-intercepts. Instead, I want to go back to something I said in the Algebra Basics unit, and that is the notion of factoring is a form of dividing. And so I'm going to do some dividing here. And I'm going to tell you that one of the factors of this polynomial, is x minus 1. So I want to think about dividing. Or you might see this notation, x to the third minus 2x squared minus 5x plus 6 divided by x minus 1. Okay? Well, we will be doing synthetic division, but we are going to start with long division because there are some things that synthetic division can't do, and we need to be able to still do. So we're going to start with some long division here. And that's what I want to do. I want to do some division to divide this polynomial by this factor as a way of breaking it down. When I can't use any of my factoring techniques, division will help me. So let's review long division. Okay, what do I multiply this x by? Don't worry about the minus 1. Just what do I multiply this x by to turn that x into an x to the third? Hey, Gabe, what do I multiply this x by to turn it into an x to the third? An x squared. Now, when I have that amount, I distribute that amount both to the x and to the minus 1. So here I'm going to have x to the third minus 1x squared. And then with long division, like we've been doing since we were little kids, with long division we always subtract. So I subtract. X to the third minus x to the third, those had always better cancel. Minus 2x squared minus a minus 1x squared. That's going to give me negative x squared. And then I bring down my minus 5x. Please note that there is lots and lots of opportunity for small sign mistakes when you do long division or even synthetic division. Okay, next step. What do I need to multiply this x by to turn it into negative x squared? Dylan? Negative x. And then I take that negative x and I distribute that negative x to both of these. And I get negative x squared. A negative 1 times a negative x is a positive x. And then I subtract. Again, negative x squared minus a minus x squared, that's negative x squared plus x squared. Those will cancel. I'll have negative 5x minus 1x, which is negative 6x. And don't forget to bring down that plus 6. And so finally, we're going to say, what do I have to multiply this by to turn that into negative 6x? And I need a negative 6 here. And so when I do negative 6 times x, I get negative 6x. And when I do negative 6 times negative 1, Gesundheit, I get positive 6. And again, I'm going to subtract. But this time, there's nothing left over. A remainder of 0. What's wrong? We're happy with a remainder of 0. In fact, we're so happy with the remainder of 0, it's got a theorem. It's called the factor theorem. The factor theorem says when the remainder is 0, the divisor, the thing we were dividing by, the divisor is a factor. It's a way we can use to confirm that we have a factor of the polynomial. Oh, look, I got a 0 remainder. Yay, this is one of the factors. Now, what do we have here really when we're done with this long division? You know, let's go back up here for a second. Here's my divisor. Here's my quotient. Well, I know if I do this problem, 15 divided by 3, I get a remainder of 0. But I also know that this times this equals that. This times this equals that. So now I can rewrite this as x minus 1 times our quotient. What was our quotient again? Well, I had an x squared, a minus x, and a minus 6. And now we're on our way to factored form. Right? That point of doing the long division, yay, we got to practice long division, but really it was to help us set up for breaking this down further. Hey, Kate, can I break this down further? How's this going to factor? X. Right, because I've got to get the minus 6. And so now I'm in factored form. So the point of us reviewing long and synthetic division is as a way of breaking down these polynomials that Brian can't factor yet. And we don't have a cubic formula or a quintic formula or a quartic formula. Okay, yet. Okay, great. Good. So long division. Now, I think it's always cool when you do lots of practice problems on your whiteboard, but we're on a Wednesday, and I still got another theorem, synthetic substitution, a whole nother division technique to do. And I still want to ask you two specific questions about long division. So we're going to be a little thin on whiteboard practice today, which will be fine for the people who are watching the video because they won't be able to do the whiteboard practice. But please be aware that we're on a sort of express train today for that reason. Okay, so now my question is this. How is this problem, 4x to the third minus 7x plus 8 divided by 2x minus 1 different? Yeah. Complete polynomial? Oh, we skipped a power. Coefficient was? So it doesn't show up. So
Just put basically like a 0x squared there as a statement.
I need to have the 0 placeholder. I see lots of people on the next test blow the problem because they don't put 0 placeholders in. No one's going to remind you about the 0 placeholders, so you might want to put a note now in your notes. Hey, look, there's no x squareds. So when I set this up with long division, 2x minus 1, I am going to do 4x to the third, as Quinlan said, plus 0x squareds minus 7x plus 8. And I'm going to go from here. Will you go from here? And then write your answer on a whiteboard. I don't need to see all the work on the whiteboard. You might want to put your work in the notebook, but I'd like the answer on the whiteboard. That was the one you did just before break. Let me know if you want to talk about that. Hi, what's up? Okay. Yeah, no worries. Mostly. Hey, have you? That's so weird. It happened again. The Chapter 3 review stations for calculus, they're not in the gradebook. But there aren't any here. But didn't people hand them in? Did you hand them in? So that's that weirdness that sometimes happens, and I don't understand it. I wish I understood why that happens, because we're all very careful people. Yeah, it's just so bizarre. Here. 5, 4. Three. 2. Is 2x minus 1 a factor of this polynomial? These people are saying no. Why, Brian? There's a remainder. And because there's a remainder, we know this isn't a factor. Now, I see a lot of people wondering, how am I supposed to represent this answer? In Algebra 2, this was the way I generally represented the answer. But right now, Mr. Kukla's talking about writing things in factored form. And he was going on about the divisor times the quotient. So according to divisor times quotient, I should have something that looks like this. I should have divisor times quotient plus remainder. So for the purposes of thinking about factoring a polynomial, I think this makes sense. But for those of you who are thinking back in Algebra 2 land, where you've got this as the quotient and you put the remainder over the divisor, yeah, I'm okay with that as the result of your long division. Okay, so if it's just a long division question, then this is a fine answer. But if we're going to be talking about a factored polynomial, then I'm looking at something like this, which highlights the fact that, no, this isn't one of my factors. I should move on with life. Any questions? Okay. What about this problem? X to the 4th minus 16 divided by x squared plus 2. X squared plus 4. Now, I hear a couple people saying, Mr. Kukla, I don't need long division here. I can factor this. Great. Use that factoring as a check on tonight's homework problems. Tonight's homework problem says you need to be doing this with long division. So let's show doing this with long division. X squared plus 4 goes into, oh, don't forget 0 placeholders. 0x to the 3rd plus 0x squared plus 0x to the 1st. Will I not need them what? I'm sorry? You know, you can put them, but we won't need them here. Where we really need them is here. But some people who are really they struggle with this algorithm, yes, it's good to put in a 0 placeholder out here too. Okay, so what do I multiply this by to turn it into this? Just an x squared. I get x to the 4th plus 4x squared. I subtract. 0x squared minus 4x squared is minus 4x squared. I bring down the minus 16. And I say, what do I multiply this by to turn it into this? Negative 4. And so I end up with negative 4x squared minus 16. And again, a 0 remainder. That's a factor. And so I could write this as x squared plus 4 divisor times x squared minus 4 quotient. And that's that difference of squares that Owen and Drew were talking about. Nathan says we're not done yet factoring this because we don't have linear factors, so we'd still need to take it further. And this is that difference of squares he was talking about. And this is coming up soon when we deal with imaginary and complex numbers. Okay, good. Any questions about long division? Long division is very, very powerful. We can do long division with polynomials here. I heard Quinlan say earlier, does that mean we're doing synthetic division? Well, yes, we will do synthetic division. I love synthetic division. Synthetic division is so fast. I agree completely with those nutsy math people who in the 1800s said this was way too time consuming. We want something more streamlined. We want something modern for our modern age. Let's get rid of all the extra writing. That's what synthetic division is all about. So let's go back and review synthetic division for a moment with this question. Oh, no, let's not do that question. That one's tough to start with. Let's start with this one. 2x squared plus x minus 3 divided by x minus 1. So, as a reminder, when I do something like this with synthetic division, things get turned around. My division symbol doesn't look the same way. In fact, here I was placing a factor with long division, but with synthetic division, it's not a factor, it's an x-intercept that goes here. So, Chase, what's my x-intercept going to be? Positive 1. So a positive 1 goes here, because that's my x-intercept. I don't use the factor x minus 1, I use the x-intercept. And because we're really trying to save writing and write as little as possible, we're not going to write all these extra symbols. We're just going to put the coefficients down. A 2, a 1, and a negative 3. And when we see this, we understand it to represent 2x squared plus 1x minus 3. Okay. So here's what we do. We start by bringing down this 2. Whatever that number is, we bring that number down. We then multiply and put the answer here. 1 times 2 is 2. Now with long division, we were all about subtracting at this point. But in synthetic division, it's all opposite land again, right? We're not using x minus 1. Chase says we're using plus 1 here. So I have to add. In synthetic division, I always add. And so I end up getting 3. Again, I'm going to multiply this 1 times that 3 and put the answer here. And again, I'm going to add. And I end up with a 0. Oh, a 0 remainder. That means that this is a factor of that polynomial. And Brian says he didn't need long division for that. He could have just factored this polynomial, and that's good. I just wanted to review synthetic with you. But we're not quite done. Let's look at this quotient down here in red. Remember how we started with x squared? This was 2x squared plus 1x minus 3, and then we divided x squared by x? So we reduced by 1 degree when we did this synthetic division. So this is now 2x. And this is plus 3. So I see this as 2x plus 3. And don't forget our divisor, x minus 1. So I'll be able to use synthetic division to get myself to this factored form as well. Any questions about synthetic division? Okay. Then will you do this one, the one we just saw a few minutes ago, 4x to the third minus 7x plus 8 divided by 2x plus 1. Oh, it was 2x minus 1. Will you use synthetic division here? There's some questions, aren't there? Yeah, what's the questions? Chase, what goes over here? Yeah, the x-intercept goes here, positive 1/2. What's the other thing I need to be mindful of here, McKenna? I need 0x squared, so this is going to be 4, 0, negative 7, positive 8. Okay. 5, 4, 3, 2. Oh, that's a minus 1. Okay. 1. So I see a lot of 4x squareds plus 2x minus 6's times 2x minus 1 plus 5's. And that's fabulous. That's great. I'm really pleased. But wait a second. When we did this problem a few minutes ago, that was our answer. So Drew says if I take his board up here, and I write down his answer, 4x squared plus 2x minus 6, he can factor a 2 out of each of these. And he's got 2x squared plus x minus 3. And over here, he's got, well, wait a second. That's not what he has. He used this. He had x minus 1/2. Now what happens when you multiply that 2 through, Drew? Now you get the 2x minus 1. But Drew, if you do this, what's 4 times 2? Is this 8? Oh, pay attention. This is what Chase told us to divide by. So this is what goes into the factor. And then Drew says, I could pull a 2 out of each of these and distribute that 2 into here. And then my answers will be the same. In fact, this one, Drew, with the x minus 1/2 times this, that works. But the 2x minus 1 and this does not work. And I saw a lot of boards with that on it just now, so watch out for that. Okay. Any questions about using synthetic division? Okay. Hi. I got 2 more things to do. Hurry. All right. Let's take a look at this. We just did this problem here. And we had this remainder, right? Okay. We said 1/2, 4, 0, -7, 8. 4, 2, 2, 1, -6, -3, 5. Okay. I want to ask a different question now. F of x equals 4x to the third minus 7x plus 8. Mr. Kukla, just coming out of the functions unit, says, what's f of 1/2? And in the functions unit, what did we do? Plugged in a half. 4, 1/2 to the third minus 7 times 1/2 plus 8. And even though everyone is too polite to do all that groaning right now, I hear all that internal groaning right now. Okay? 1/2 cubed is 1/2 times 1/2 times 1/2, which is 1/8, minus 7/2 plus 8. And this is just going to be 1/2 minus 7/2, which is minus 6/2, plus 16/2, which is 10/2, or what? That was so cataclysmic, they had a parade in Austria for it. And they named it the remainder theorem. See, over here in function land, we know that f of 1/2 equals 5 is an ordered pair on the graph. With this x value, we get this y value. Well, I can find the same thing without having to stress over all those fractions. no fraction stress. All I'm going to do is this cool thing called, it's got a name too, it's called synthetic substitution. Instead of doing f of 1/2 by doing 4 1/2 to the third minus 7 times 1/2 plus 8, instead I do 1/2, 4, 0, minus 7, 8, and I whip through that and there's my answer. And synthetic substitution is so much faster than this functiony way of doing. Okay? So I really like synthetic substitution for this. But wait, that also brought us to the remainder theorem, didn't it? What was the remainder theorem? The remainder theorem says the remainder is the y value for the x value of the divisor. So whatever I'm dividing by, this x value, that's going to be the y value. And that's why the factor theorem works, right? Hold on. When the remainder is 0, the y value at that point must be 0. And what's the y value for every x-intercept? 0. So actually the factor theorem came after the remainder theorem. The remainder theorem first to show that that remainder shows up as a y value on the graph, and then the factor theorem later on to say, oh look, here's a special case. When the remainder is 0, the y value on the graph is 0, and therefore you have an x-intercept, so you can make factors. Any questions? Okay. We've got factor theorem. We've got remainder theorem. We've got synthetic substitution. We've got long division. We've got synthetic division. That's a bunch of stuff on a Wednesday. And we still got 3 minutes. On a piece of paper, please write down what the factor theorem is, what the remainder theorem is, and provide an example of each. Or provide some math to back up what you're talking about. Don't forget to put your name on this piece of paper. And we're turning it in. And it'll be strange if your examples look like your neighbors'.